100 samples were drawn from a production process. Each after 5 hours. The number of defectives in these samples were noted. The number of defectives in these samples were noted. A Poisson distribution by estimating the parameter m. A Poisson distribution by estimating the parameter by recall that in Poisson distribution the formula is e to the power minus z into z raised to m. Oh, sorry. Okay. So by estimating the parameter m, was fitted to this data. Was fitted to this data. The results obtained the results obtained are number of defectives, number of samples, so observed, expected number of samples. So the data is 0, 1, 2, 3, 4, 5 and above. $63, 28, 6, 2, 1. Oh, done it wrong. 28, 6, 2, 1, and 0. Expected number. Look, the expected number is calculated using this Poisson's distribution. Yes, I was recalling this. What was the formula? E to the power minus m into m raised to r by r factorial. This was the formula for the Poisson's distribution where m was the mean. So this mean is estimated here. Okay. So the expected number 60.65, 30.33, 7.58, 1.26, 0.16, and 0.02. Test the goodness of fit. Fit of Poisson distribution. In bracket level of significance 5%. What is our null hypothesis in this case? H naught is that Poisson distribution fits good. Poisson distribution fits good. H1 fitting of Poisson distribution is not proper, or the Poisson distribution does not fit good, or the fitting of Poisson distribution is not proper. Next thing, recall the remark. If in some class you have the frequency less than 5, then what we have to do is we need to add it to the previous classes. Okay, so we just look at the observed and expected frequencies here. So you can see that this is less than 5. So we have the less than 5 frequency. So what we will do is we need the expected frequencies. Okay, so here we pool here, we pool expected frequencies until their sum is greater than 5. Until their sum is greater than or equal to 5. And also we pull observed frequencies. Okay, so the new observed frequencies and expected frequencies. Observed frequencies and expected frequencies. So the observed frequency for the first class was 63 and expected frequency for the same class was 60.65. The second class was 28 and expected was 30.33. So both of the expected frequency is greater than 5. So what will happen is, now expected frequencies here are less than 5 for the last 3 classes. So you go on adding it to the previous one. So 0.02 added to 0.16. So that will be 0.18 and that will be added to the previous one, which is 1.26. So 1.26 plus 0.18, still the value that you get is 1.44. This is still less than 5. So what we do is we add this to the previous class. So 7.58. So that will be, so the total will be 9.02. Okay. So expected this 9.02. So add the corresponding observed frequencies 0 plus 1 plus 2 plus 2 plus 1 3 and the 6. So that will be 9. I hope the method is clear. Now let's define the use of test statistic. We use the test statistic. So what we are using here, chi-square. Whatever test you are using, that is nothing but the test statistic. So in this particular topic, we are using chi-square test. So the formula that we saw was summation OI upon EI whole square. Sorry, not whole square. Simply OI square. OI square minus N. What was N? N was the total frequency. Total frequency in the question itself, it was given that 100. So I is running from 1 to K. So now, how do you define the degrees of freedom? Let's recall. K is the number of samples. Okay. So we have, random variables. So 1, 2, and 3 classes are there. P, the number of parameters, those were estimated. So estimated number of parameters. So in the question itself, it was given that we are estimating the parameter M. So the value of P is 1, the value of K is 3. And this N is the total number of samples, so it is 100. So note that K is equal to 3, P is equal to 1, and this value also will need N is equal to 100. So if you are not comfortable with this n, you can also use the same formula that we did earlier, summation OI minus EI whole square divided by EI. I is running from 1 to, in this case, 3. So this is also workable, okay? There's no problem in this. So 3 minus 1 minus 1. So that will be chi 1 square is equal to, do the summation, OI, that is 63 square divided by 30.33. 63 square divided by 30.33 plus the second one, 28 square divided by, this is 60.65 actually. This is 30.33 plus 9 square divided by 9.02 minus 100. So chi-square distribution with 1 degree of freedom, that is 100.27009 minus 100. So which gives me chi-square distribution with 1 degrees of freedom, that is 0.27009. The tabulated value, note that the degrees of freedom and level of significance is 5%, so that will be 0.05. So tabulated value is 3.841. This is stable value. What do we see? So the calculated value is less than the tabular value. So what is our conclusion? Accept the hypothesis. We accept H naught at 5% level of significance. Give an example, I'll give it as a homework. Among 64 of springs, of a certain cross between guinea pigs 34 were red, 10 were black, and 20 were right. 20 were white. According to genetic model, according to genetic model, these numbers should be in the ratio. These numbers should be in a ratio 9 is to 3 is to 4. Are the data consistent with the model? At 5% level of significance. So here there is no probability distribution given, okay? So what you are just looking at is corresponding to that genetic model, we are given the ratios. So if in this case the observed frequency for the red pigs were 34, that has to be the I mean 34 and 10 black and 20 were white. So these three numbers, according to these three numbers, the model should give it in the ratio 9 is to 3 is to 4. So as we can see, so total is 9 and 4, 7 and this 16. So expected frequency has to be 9 upon 16 into how many crossbreeds were there? 64. So 9 upon 16 into 64 will give me the frequency for the expected frequency for the red pigs. Similarly, 3 upon 16 into 64 will give me the expected frequency for black pigs, and 4 upon 16 into 64 will give me the frequency for this expected frequency for white pigs. And once we have both these data, then you can go ahead the expected tabulated value table value for chi-square distribution with 2 degrees of freedom 0.05 is 5.99. So you can do the further calculations and decide whether the given hypothesis has to be expected or accepted or rejected. So I'll start with the new point, that is testing of hypothesis using T distribution. Test for population mean using T distribution. So first of all, we will look at the theory part behind this. So in this case, we are going to test for population mean. Okay. In the previous case, we were looking at the fitting of a particular distribution, but here we are not going to look at the distribution, fitting of the distribution. We are going to look at the population mean, whether the null hypothesis is the mean of the given data is something, and we need to check whether the mean is as expected or not. Okay, so in this case, let x1, x2 dot 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 till xn be a random sample of size n. From a normal population, from a normal population. With mean mu and variance sigma square. Our H naught in this case is, the null hypothesis is that mean of this population is mu naught, and my alternative hypothesis is that the mean is not equal to mu naught. So there are two cases in this. In some example, sigma square will be given to us, and in some example, sigma square won't be given to us. So if sigma square is given, then u is equal to x bar minus mu naught divided by sigma upon under root n, small n. What is small n? Small n is the number of samples that you have. Okay. So we'll find out the value of u, and depending on this value of u we will sorry, this has to be T naught. Is this. So x bar minus x bar minus mu divided by sigma on root n. Okay, and in the cases where the sigma square is not given, so case number 2, what we do is we use the formula. So if sigma square is not given, then we use the formula x bar minus mu divided by s upon under root n, where s square is given by summation x minus x bar whole square divided by n minus 1. So here in this t is equal to x bar minus mu divided by s upon root n. This is t distribution with n minus 1 degrees of freedom, with n minus 1 degrees of freedom. Thus in this case this follows normal distribution with 0, 1. So fine, then we will stop here. In the next lecture we will solve some examples on this distribution and that on this hypothesis testing. Okay.